This is Paul. His online store takes 2 full seconds to load a product page, so he added Redis. And now the store lies about prices instead. Nothing crashed. That's the scary part.
I'm Taha and I have a solution for you.
By the end of this video, you'll be able to explain everything Paul is about to live through. This is caching, the whole map, 11 concepts. 2 of them explain why caching works, and 5 explain how it breaks, and the one at the bottom decides whether Paul's next traffic spike is a normal Tuesday or an incident report. We start exactly where his trouble started. Chapter 1. Paul runs a small online coffee store where every product page needs a database query that takes about 200 milliseconds. That was fine at 10 visitors an hour. Then his Grindr review went viral, and 1,000 people opened the same page in 1 minute, so his database built the same answer 1,000 times for data that never changed. Paul does the obvious thing and saves the answer. He keeps a copy of that page in Redis, somewhere faster and closer than the database, and serves the next 999 shoppers straight from memory in under a millisecond. That copy is a cache. And notice what it did not fix. The very first request still paid the full price, because a cache can only return what somebody already asked for. Caching never makes one fetch faster. It makes repeated fetches faster, and that only pays off if people keep asking for the same things. Why would they? That's Node 2. Node 2, Locality of Reference, the reason caching pays at all. Paul's traffic looks random, but it isn't. The same 20 bestsellers get hammered all day long, and whoever views a Grindr views the matching scale a minute later. That pattern has 2 halves. Temporal locality means whatever was touched recently gets touched again soon, and spatial locality means the neighbors get touched next. Every cache on Earth is betting on those 2 habits, and the bet runs deeper than Paul's store. Inside his laptop, the CPU pulls memory in 64-byte lines of 16 integers, so reading element 0 drags 1 through 15 along for free. Paul once benchmarked a big matrix, walking down the columns instead of across the rows. Same data and the same amount of work, and it ran 9 times slower, purely for touching memory in the wrong order. A cache is a bet that the near future looks like the recent past. Every lookup either wins that bet or loses it, and both outcomes have names. Hits and misses. Every lookup Paul store makes ends in one of exactly 2 ways. A hit means Redis has the copy and answers in about a millisecond, and a miss means it doesn't, so the request falls through to Postgres and pays full price. Paul used to read misses as failures, and that's the wrong model. A miss is an instruction. Go get it. The store fetches the real answer and writes it back into the cache, so the next shopper gets a hit. That pattern is called cache aside, where the application fills its own cache, which means misses are literally how a cache gets filled in the first place. It also explains Paul's scariest Friday. He deployed at 9 and the cache restarted empty, so every request missed at once, and the whole morning rush landed on Postgres like a stampede. Not a bug, a cold start. Now Paul warms the cache before every deploy by preloading the 20 bestsellers before the crowd arrives. So the cache works. How does Paul prove that to his boss? 1 number. Hit ratio. Out of all the lookups, the share that were hits. Paul's dashboard shows 95%, and when he proposes pushing it to 99, his boss shrugs because 4 points sounds like nothing. Paul explains it the right way around. Latency doesn't care how often you hit, it cares how often you still pay the miss penalty, and a miss costs about 100 times a hit. Going from 90 to 99 means paying that penalty 10 times less often. Same 4 points on a dashboard, 10 times fewer slow requests. And this number has 2 parents on the map for a reason. Misses define the ratio, but locality decides it, because the ratio is really just Paul's traffic pattern measured, which is why buying more memory so often buys nothing. More RAM cannot cache a future that never repeats itself. Fine, the number is green and the cache is winning, right until the cache fills up and something has to die. Eviction. Paul assumed a full cache deletes whatever went stale, and that's the wrong problem entirely. Eviction is about space, not staleness. When the cache is full and something new knocks, a perfectly fresh entry has to die to make room, and choosing the victim is a bet on the future. The provably perfect policy does exist. Evict the entry you won't need again for the longest time. It just requires seeing the future, so it survives only to make every real policy feel inadequate. Paul gets 3 ways to guess. FIFO evicts the oldest entry no matter what, which is how his config object read on every request got thrown out for the crime of being old. FIFO is blind to access patterns. LRU evicts whatever went longest untouched, the locality bet again, and it served Paul beautifully until a nightly export scanned a million rows once and flushed his whole hot set out the tail. And LFU keeps whatever is most popular, which is why last month's viral espresso video camped in the cache for weeks on past glory. Every policy is a bet, and every bet has a nightmare workload. And eviction was only the easy half of forgetting. Cache invalidation, the one they warn you about. Paul assumed that when the database changes, the cache somehow finds out. It doesn't, and nothing tells it. During the spring sale, marketing dropped the price from $20 down to $15, and Paul's cache kept selling at $20 to every single shopper. Fast, confident, and wrong. There was no error and no crash, because a stale read looks exactly like a correct one, and support got the angry emails long before Paul got a single alert. That silence is the entire danger. Invalidation is the job of noticing a copy went bad and killing it, and it's famously one of the 2 hard things in computer science, because doing it right means catching every path that writes the data and every layer that holds a copy. Miss one and the fast system you built becomes a slowly lying one. So how does Paul cope? 2 ways, with a timer and with a promise. Time to live. Paul stamps every cached price with an expiry of 60 seconds, and he understands exactly what that buys. TTL does not keep data fresh. It puts a ceiling on how long he's willing to be wrong. If a price changes 1 second after the copy was cached, shoppers see the old number for 59 more seconds, and the cache has no idea. TTL never asks whether the data changed. It only asks how much staleness you can live with, eventual consistency on a timer. And Paul can't just set it to 1 second, because every expiry is a future miss and a tiny TTL trades lying for a database beating. For the one field where wrong is unforgivable, the shipping address at checkout, Paul uses the strict option called Write-Through. Every write updates the cache and the database together in one synchronized move, and neither side is done until both are done, the cache that never lies. The bill is real, because every write now does double work. That kept one machine honest. Zoom out, and it was never just one machine. Layers. Between a shopper and Paul's database, there was never one cache. There are at least 4. The browser keeps copies on the shopper's own laptop, the fastest possible hit, and it helps exactly one person. The CDN edge holds copies near whole cities. The Redis box Paul thought of as the cache holds his computed pages, and Postgres itself keeps hot rows warm in its buffer pool. A request falls through those layers in order, and the deeper it falls, the more it costs. The browser layer even runs on a written contract. Paul's server tags every response with max age 3600, which means trust this copy for an hour, plus a fingerprint called an e-tag. When the copy expires, the browser doesn't re-download the megabyte of JavaScript. It asks whether the fingerprint changed, and the server answers 304 with no body attached, so the whole transfer collapses into a few hundred bytes. Stale doesn't mean wrong, it means unverified. One of these layers deserves its own chapter because it's the only cache that fights physics. A CDN is not a faster server. It's a nearer one. Paul's first customer in Sydney taught him that because her phone talked to his server in Virginia across 15,000 kilometers each way, and at 2/3 the speed of light, that round trip burns 150 milliseconds before a single line of Paul's code even runs. No eviction policy fixes geography. So a CDN copies his images and scripts onto hundreds of edge servers around the planet and serves every visitor from the closest one, which puts most of humanity within 50 milliseconds of a copy. And yes, the first visitor in Sydney still waited the full 180 because an edge fills on demand and a miss is how caches fill. Physics just hasn't been cached yet. Layers beat distance. But when Paul's traffic outgrew one cache box entirely, stacking stopped helping, he had to shard. Distributed caching. One Redis box has a memory ceiling and a throughput ceiling, and Paul's growth curve respected neither, so he sharded 4 nodes where every key lives wherever hashmod 4 says it lives. 4 times the memory and 4 times the throughput, plus one brand new question no single cache ever had to answer. Which node holds this key? Every client must compute the same answer every time, and Modulo does exactly that, flawlessly, right up until the day Paul added a node. Black Friday was coming, so he scaled 4 nodes to 5, and the rule silently flipped to hashmod 5, which sent almost every key in the fleet to a different node. The data was still sitting in memory, but nobody looked in the right place anymore. Paul cold started his own cache at the worst possible moment, a self-inflicted fleet-wide stampede, where adding capacity is what caused the outage. The fix is the smartest idea on this whole map, and it's the last node. Consistent hashing. The reason adding a server doesn't melt a cache. Paul's problem was the divisor. Mod 4, Mod 5 change the n, and every remainder changes with it, so consistent hashing throws the divisor away. Picture the hash, space bent into a ring. Every node sits somewhere on that circle, and every key belongs to the first node clockwise from where it lands. When Paul adds node 5, it claims one arc, the slice between itself and its neighbor, and every other arc stays exactly where it was. Modulo moved nearly 9 keys in 10, while the ring moves about 1 in n. At 100 nodes, that's 1% instead of 99. One refinement makes it fair, because each machine appears at 100 or so virtual points around the ring, so the load spreads evenly. The idea came out of MIT in 1997. A little company called Akamai was founded on it. And for Paul, it's the difference between adding capacity as a one-line stand-up update and adding capacity as the title of a post-mortem. Look at the map, because Paul's whole year is on it, and now you can explain every node. The copy and the bet it rides on, hits and misses, and the one number that rules latency. 3 ways to forget, the lie a timer merely bounds, and the right that never lies. The stack of layers, the cache that beats light, the shard, and the ring that saves it. That's 70% of caching, a working model of every node on this tree. The last 30% is reps, actually invalidating things, actually tuning things, actually breaking things. Caching, 18 lessons on iCommit. Go earn the rest.